There we go. There we go. Gotta use the fuck.
No, I'm just not talking.
Oh, my
Not
bad.
11 o'clock yet.
Yeah. There you go. There you go.
Okay, now it's 11 o'clock. Jeff, can you mute your microphone? You got someone in the background. Or maybe that's Evan. Not sure.
So like, oh, I see. Like target him. Yeah, exactly. Fuck up.
Never mind. I can do it for you. All right, 11 o'clock. Let's get started. So last class, we introduced the diffusion equation. We derived the diffusion equation from the principle of conservation of energy. And we combined the manipulated principle of conservation of energy. We defined that in terms of some little small domain, which we called omega. And then we did some math on it and showed that we could obtain an expression that was true pointwise. And then into that expression, the conservation of mass expression, we added what we call the constitutive relation, describing the flow of heat. That heat flows downhill at a rate proportional to the gradient of temperature. And that actually, I should have pointed out, that has a name. That's called Fourier's law of heat conduction. And when we inserted Fourier's law of heat conduction into the conservation of energy equation, we got the diffusion equation, okay? Which is right here. There can be a source term. We can call that F. That source term can depend on both X and time in principle. Now, before we really get started trying to solve this, I want to make some general observations about it. First of all, the new feature is we have both time derivative and space derivatives. We have one derivative in time, we have two derivatives in space, and it's no longer possible to solve this using methods from ODEs, all right? So we did all this work beginning of the semester, we did all these problems, and many of them were very easy to solve using simple methods from ODEs, although as we got towards the end, it got harder and harder to solve those problems using direct methods. Now there are no direct methods, all right? There's no way to sort of manipulate this to get a simple closed form solution. And so these eigenfunction expansions are one of the only methods that we have. What else can we say? Whenever we have differential equations, we expect initial conditions or boundary conditions. We saw that with two space derivatives, a second order spatial differential operator. We had two boundary conditions, typically one at x equals 0 here and one at x equals L. Well, when we throw an extra time derivative into the mix, what's going to happen is that we also need one condition in the time direction. And the way to sort of picture this is through what we call a spatiotemporal diagram. All right, so this diagram right here represents the solution domain, okay? And in the horizontal axis, I have x for space, and in the vertical axis, I have t for time. Where does the solution exist? Well, if it exists on some domain, like we've been doing, x might go from 0 to L, oftentimes L is 1 for simplicity. And then time typically begins at t equals 0. And then in principle, it just extends forever into the future, all right? So once I start up a heat conduction problem in motion, it just goes and goes and goes, and there's no cutoff time that physics forces this problem to stop evolving, right? It may eventually evolve towards a steady state, but then that steady state will persist for all time. Okay, so there is no upper boundary on time. And so what we have, the domain for this problem is this region in here, in this spatiotemporal diagram. Okay, and if you look at this thing and you just sort of keep track of where are the boundaries in the sort of generic sense with quotes around them, we have spatial boundaries. We have a wall on the left-hand side and a wall on the right-hand side. And so it makes sense that we need two boundary conditions, one on each side. And then we have a new boundary because of the time dimension. We need a condition over here to sort of describe what's happening at the beginning. All right. So what's going to happen is that we actually now have three conditions that we need to write down. We might have like a boundary condition that might take place at x equals 0. And then we might have a second boundary condition, possibly involving u and ux, that takes place at x equals L. But now we're going to have an initial condition, typically just involving u, that takes place at t equals 0. Okay, so there'll be three sets of conditions every time we study a diffusion equation. One for the one derivative in time, two for the two derivatives in x. All right, so that's one thing that it's important to cover. Now, qualitative expectations. How do I expect the diffusion equation to behave? This is worth thinking about, and we can think about it from two perspectives. One, imagine I have an initial condition. Again, I've got some bar, that I'm interested in understanding the temperature in. And at some point, I build a fire under this bar, or I stick it over a flame or something. And so I have a temperature distribution in the bar that may look like this. Okay, and then I turn off the fire. I turn off the fire and I start the timer, and I'm interested in how this function evolves. All right, and this is the function u of x and t that we're interested in understanding. What does your intuition say is going to happen to it? And suppose at time t equals 0, we put the edges of the bar in chunks of ice. What do you expect is going to happen to this over time? And why?
But the edges of the bar would heat up due to conduction from the middle of the bar.
The edges of the bar what?
Would heat up over time. The temperature would raise due to conduction from the hot middle of the bar.
Okay, so the edges might warm up due to conduction. Actually, if we encase the edges in ice, all that heat will flow that might be flowing to the edges of the bar will flow into the ice, and the edges won't necessarily heat up at all. And so you might have if you have a boundary condition, u equals 0 on both sides, then that forces the temperature, by virtue of being locked in a block of ice, that forces the temperature to be 0 on both sides. So there is conduction, but that doesn't necessarily mean that the edges will warm up if they're encased in ice. But what happens if heat flows from the middle to the edges, which you're right, and why do you say that? What gives you that intuition?
Heat and mass transfer.
Okay, all right. Your heat and mass transfer class. And we know both maybe from classes, but also just from experience, that heat flows from regions of hot to regions of cold, right? So what's going to happen? If I were to sketch what this looks like in 1 minute. Okay, we expect heat to flow this way. The curve will flatten. Flatten the curve. Hashtag flatten the curve. But the edges will come up. No, the edges will not necessarily come up if they're encased in ice. This condition right here is like forcing the temperature at the edges to be a certain thing, such as by locking them in a big block of ice. Now, if we had a different set of temperatures, remember, we said that the heat flux J was proportional to negative dt dx times K. So what if I had a Neumann condition? What kind of condition? What would that be saying? If I have a Dirichlet condition, that's like saying the temperature at the edges must be something, right? Because I've got a huge reservoir of something like a block of ice that can keep the temperature at that level. But if this is how heat flows, this is my Fourier's law of heat conduction. What does a mathematical, this is a physical statement, what would a mathematical statement like this imply physically?
That the heat would not change with X.
The heat would not change what?
With X?
Right. So that's the mathematical statement. Let's see, no temperature change at the boundaries. Remember, what does the slope of the temperature correspond to? The slope of the temperature is proportional to the heat flux. And so if I'm forcing the slope of temperature to be 0, what that really means is happening physically is there's no flux. Okay? And those of you who have taken heat and mass transfer in the text box, what is it when I don't allow heat to pass through something? What do I call that?
Isothermal.
Okay, isothermal, adiabatic. I guess, yeah, those are fine. The word I'm looking for is insulated, right? So if I've got like a big thing of insulation here, then heat can't go. Yeah, heat cannot pass through. And so a Neumann condition in the context of heat flow is an insulating condition, right? So that would be like perfect insulation. And if I had perfect insulation, then yes, heat cannot get out of the bar. And so when it flows from the center to the edges, the temperature at the curves would come up. Okay, but I'm getting ahead of myself. Right now I've got Dirichlet conditions, U equals 0. What is going to happen to this temperature profile? Heat flows from the center to the edges, and then it flows out into the ice block. And what happens over time?
It goes to 0.
Eventually it goes to 0. All right. But it doesn't go to 0 immediately. It's gonna gradually decay, right? And so the temperature is going to drop and drop and drop. All right. So we can infer something like this just from Fourier's law. The heat flows from hot regions to cold regions, and the steeper the slope, the faster the heat flows. So we might expect that at the beginning, the temperature drops rapidly. Okay, here's a rapid drop in temperature over the first time unit. But then over the second time unit, well, okay, it still looks rapid. But then over successive time units, the drop gets slower and slower, right? Because the slope, I'm sorry, I can't draw. The slope is getting smaller and smaller, so the rate of heat flux is getting lower and lower. And so this whole process sort of slows down as we get closer and closer to a uniform heat distribution. Okay? So that intuition can all come from Fourier's law of heat conduction right here. We could, however, have gotten a quite similar intuition if we just looked mathematically at the structure of the equation, right? This says the rate of change of temperature equals UXX. But what geometrically does this correspond to? UXX. Concavity, right? And so what this statement says is that the more concave something is, the faster it changes. Okay, if I have an initial distribution that looks like this, the concavity is negative, it's concave down. Okay, and the steeper this thing is, the more negative is UXX, the faster the temperature is going to decline. As this then decays, all right, the rate of change of temperature will get slower and slower. Okay, and so we could also have maybe anticipated some sort of behavior like this just from looking at the mathematical structure of the heat equation itself. All right. Good. So now that we have set these expectations, let's do an example problem. So here we have our first partial differential equation. UT equals UXX. I've got an initial condition right here. That the initial condition is that the temperature is 30 degrees. That's like room temperature. Okay. And then note that my boundary and initial conditions now have two arguments. Okay. So my initial condition takes place at t equals 0. All right. But all values of x. So this is in principle a function of x, and I've just chosen it to be some constant function of x. On the other hand, the two boundary conditions take place at the left and right hand sides, but they're true for all time. And in principle, they can be functions of time, right? I can manipulate the temperature at the boundaries over time, and that is perfectly acceptable if this is a function of time. But for simplicity, for our first problem, I've just set them equal to 0. I've also, for simplicity, I don't have any kind of forcing function here, all right? We'll get to that pretty quickly, actually. All right, so you might be thinking to yourself, all right, this is quite a bit different. I'm not exactly sure what to do, but does anyone want to take a guess what we can do? I swear you already know how to do this problem. Did anybody try it? Any guesses? How have we solved every problem we've done so far in this class? We would split it under which conditions? When would we split the problem? That's correct. And are there non-homogeneous boundary conditions in this problem? There are not. So what if there were no non-homogeneous boundary conditions, what did we do?
Project onto eigenfunctions.
We found the eigenfunctions, okay? Jump straight into finding eigenvalues and eigenfunctions. And the whole point of finding eigenfunctions, one way of thinking about them is that they turned something hard into something easy, right? They turned a differential operator into multiplication by a constant. What if we could turn this into multiplication by a constant? Then we would just have an ODE in time, which is what you spent your whole ODEs class solving. Do we know how to turn that UXX into a constant, into multiplication by a constant? We do. How do we do it? What do we have to do to this problem? What action must we take on this problem in order to make that UXX turn into a constant times something? We take the transform. All right, that's exactly right. So we're going to take the transform of this problem. And what is the transform for this operator that I have circled? we want to find a transform such that the transform of uxx becomes minus lambda sub n u sub n. Okay, that'll replace a differential operator with a multiplication by a scalar. And we've actually already done this, all right? We did this a long time ago. We're going to find eigenfunctions. Such that phi xx equals minus lambda phi, subject to what boundary conditions? Oh, these boundary conditions. And we've done this problem before. All right, I wanna skip the details. We have already done this. These are the eigenvalues. These are the eigenfunctions. All right, and the transform is 2 integral from 0 to 1 of whatever this is times sine n pi x dx. And the inverse transform is the sum n equals 1 to infinity, the coefficients times sine n pi x dx. We've already, we know this operator is self-adjoint. We know it has a weight function of 1. And so all of that sort of complicating stuff is sort of missing. This was one of the first problems we ever studied. We find the eigenvalues and the eigenfunctions. We define the transforms, all right? So what happens when we take the transform of this problem? What we want to do is take the transform. Remember, another way to think of transforms is that transforms convert a function of x into a quote-unquote function of n, where n is a discrete set of numbers instead of a continuous variable x. So anything that has an x in it, we want to take the transform of. So specifically, we take the transform of the PDE, okay, and we'll have to figure out what all these things mean. But in addition, there's a new thing that depends on x. Oh, sorry, no, we don't. There's a new thing that depends on x, and that's the initial condition. Okay, this right here is a statement involving a function of x. This left-hand side is a function of x, and this right-hand side is in principle a function of x. It's a constant function of x. So we also need to take the transform of the initial condition, right? U of x comma 0 n equals the transform of the right-hand side, 30. Okay, now, what does all this mean? It's not exactly clear. We know that the transform of uxx is what? This we've seen before, and so we know what this is. Because this is a uxx, the second derivative is a self-adjoint operator, and we take the transform of a self-adjoint operator, we get, yes, we get minus lambda sub n u sub n. And the transform of 30, we know how to do that. That's 2 times the integral from 0 to 1 of 30 times sine n pi x dx, which is 60 times negative cosine n pi x over n pi from 0 to 1, which is 60 over n pi times 1 minus cosine n pi. Okay? But what is ut n. What's the transform of the time derivative of u? I don't have like a fancy rule yet to understand, so I just have to do it. Okay, so how do I do it? What does it mean to take the transform? Okay, that's right. Inner products. And so that denominator is a half, and that's where that 2 comes from. So it's 2 integral from 0 to 1 of du dt times sine n pi x dx. Now, I don't know what u is. That's the whole thing I'm trying to figure out. So I cannot just evaluate this. But we actually encountered this kind of idea when we were deriving the diffusion equation. Here I have an integral over x of a derivative with respect to t. What is something I am allowed to do with that? We can take the time derivative outside the integral. Since the integral is over space and the time derivative is over time, and x and t are independent variables, we can exchange the order of operations using Leibniz rule. And again, these boundaries don't depend on t, so there's nothing really complicated. We can just straight up switch them. When we do that, if we pull that time derivative outside, we will have already taken the integral with respect to x. So the remainder thing will only be a function of time, so it becomes an exact full derivative. And so I have here 2 times the integral from 0 to 1 of u times sine n pi x dx, okay? But then notationally, what is this? What is this thing? What is another way to denote this quantity? I pulled that time derivative outside, and like, what is this operation? What am I doing to u? Yep, it's the inner product of u and our eigenfunction divided by the inner product of the eigenfunction times itself. And we call that operation the projection or the transform, okay? This is nothing more than the transform of u, okay? And so this whole thing can be written dun dt, okay? So what this says is that the spatial transform of ut is equal to the time derivative of the transform. And that's just, again, it's this principle of interchanging the integration and the differentiation in time, okay? We just switched to integral notation to help us figure that out. But you can absolutely basically swap the sub n and the sub t here, and you get this. So we don't know what this is, but we know that it can be written alternatively in this way, dun dt. And finally, let's think about the transform. I have this statement on the left, u of x comma 0 transform. What is that? Well, one way I can think about that is to say that one way I can think about u x comma 0 is to say that it is u of x comma t at t equals 0. And again, what I have here is two separate operations. I have taken integral in x, and then I have evaluate the result at t equals 0. But again, since x and t are independent variables, I can exchange that order of operations. I can say first, do the integral of u, and then evaluate the result at t equals 0. And again, this thing right here is just u sub n, the transform of u. And so what I'm really doing here is I'm just evaluating un at time t equals 0. So if I put these four pieces of information together, then my transformed PDE looks like this. And this, my friends, is just an ODE, and you solved it in the first week of ODE's class. So these transforms that we've been learning about all semester to apply to boundary value problems can directly be applied to partial differential equations with this structure. And they turn our partial differential equations into ordinary differential equations. Just like they turned a boundary value problem into an algebra problem, they turn a partial differential equation into an ordinary differential equation. All right, and these can be easily solved, all right? This is a simple homogeneous first order ODE. I can rewrite it in standard ODE form plus lambda n u sub n equals 0. And it has solution e to the minus lambda sub n t times a constant. Okay, and how do I find that constant? I plug in my initial condition, and I get un equals, un of 0 is C1, which has to be 30 sub n. And so u sub n of t is 30 sub n e to the minus lambda n t. There's my solution. So I take my transform, I solve, and what happens after I take the transform and then solve? I take the inverse transform. Okay, and if this is my solution in the transform space, in the eigenfunction space, then my solution in real space is going to be the sum n from 1 to infinity of that. And let me just rewrite the actual values here. It was 60 over n pi quantity squared. No, 60 over n pi. 1 minus cosine n pi times e to the minus, what was lambda sub n? That was n pi quantity squared, n pi x. And that is my eigenfunction solution to this diffusion equation. Let's watch a movie of that exact thing. All right, let me bring it back and let me freeze it. Okay, so a couple of comments. Here's my initial condition, or at least my attempt to represent the initial condition. You'll see that it has a lot of Gibbs phenomenon going on, and I'll talk about that. But for the moment, ignore that Gibbs phenomenon and just imagine that this is a straight line that goes instantaneously from 0 to 30, and then it's a straight line 30 across the bar, and then drops down back to 0. If I included enough terms, I could make this look more like it. I didn't try too hard to eliminate Gibbs phenomenon. or I mean, shove it to the edges like you can do. After just one little time step, why is it not changing? Come on. Very disappointing. Why is this not working? It worked once, I swear. Okay, having some technical difficulties here. What I want to try and represent is that almost immediately it smooths out, the Gibbs phenomenon goes away. We'll talk about that. And then let me just play this a few times. What you see is that first you see some very rapid decrease in temperature by the edges. I wonder if being maximized is causing problems. All right, I'll put it on repeat. Rapid loss of temperature at the edges, and then the whole thing starts decaying, but it slows down, right? As it gets closer and closer to being flat, it slows down, and that's what we expected. The concavity is decreasing, the slope is decreasing, and so the heat is conducting at a slower rate, and so it's behaving kind of exactly like we anticipated. Another thing I want to mention is that as time progresses, this starts to look a lot more and more like a simple parabola or a simple contour of a sine curve, right? Very quickly, it has a very simple shape, as opposed to the very early times, the shape can be quite complicated with rapid changes near the edges and then remaining nearly flat at the interior. See if I can. Okay, nope, it's not working. Oh, wait. What if I pause? What if I pause it? Ah. Nope, I got nothing. I wanted to pause it at like the second frame, where I'll just come back to the graph over here. At like the second frame, the solution looks like this. Okay, it's still pretty flat. That's not real. That's just me, my hand shaking. It's pretty flat on the top, and then it rapidly decreases at the bottom. Okay, and that reflects that at very small times, I start with a temperature of 30 up here, but 0 down here, and that's a very large slope. And so the heat flows very quickly from the warm areas into the boundary. Okay, and it hasn't yet really had a time to affect the behavior at the middle. But before too much longer, it looks nice and smooth like a parabola or a little lump of the sine function. JC, I do see your question, and I will come back to that in a minute. So to explain what's going on here mathematically, or to illustrate the origins of this sort of interesting behavior, I want to look at the structure of the eigenfunction solution here. Okay, so first of all, it's made up of a bunch of sines, right? And those sines oscillate more and more rapidly as n increases. When t equals 0, this exponential term is just 1, right? And I'm left with, at t equals 0, 60 over n pi times this thing times sine n pi x. Well, at t equals 0, how does this series decay? In n. Right? I would cover up this term because it's just 1. And so the decay rate in n would just be (1 over n), right? Right here, 1 over n. And 1 over n, we know, does not decay very fast. And in fact, geometrically, graphically, we sort of expect 1 over n to correspond to Gibbs phenomenon. That's exactly what we saw in the movie, is we saw this Gibbs phenomenon, overshoot, lots of oscillations, okay? And so that is true. This solution, you could argue, is just a tiny bit unsatisfactory in that at t equals 0, we're trying to explain a jump discontinuity with eigenfunctions that don't have it, okay? It's really, this solution does have that jump discontinuity at time t equals 0, going from 0 immediately to 30. And so in that sense, it's a little bit unavoidable. But look what happens as soon as t leaves 0, then this term is no longer 1. All right? And if t is constant, even if the t here is small, then what I have in terms of my series in n is e to the minus n squared, which is very rapidly decaying in n. So for any t other than t equals 0, this series decays very rapidly in n. Faster than any negative power of n, it is exponentially decaying in n, which is just, very, very quick. And that's why we saw, or didn't see, as the case may be, because I couldn't get my movie software to work, that as soon as t became just the smallest bit above 0, that solution got really nice and smooth. Okay? So that's one thing I wanted to point out about the structure of this solution. The second thing I wanted to point out is that each of these modes, we could call them, each of the eigenfunctions, decays in time at a different rate. So we now have all these different eigenfunctions in our initial condition, and they're all decaying in time because of this exponential decay rate. But look how the rate changes depending on the value of n. Okay, small values of n decay with a given with some speed, but if I go from n equals 1 even to just n equals 2, then this term right here quadruples. And that mode, the n equals 2 mode, decays 4 times as fast as the n equals 1 mode. The n equals 3 mode decays 9 times as fast as the n equals 1 mode. The n equals 4 mode decays 16 times as fast as the n equals 1 mode. And so before long, all of your modes have basically disappeared except n equals 1, right? And that's why this other feature of the solution shows up, which is that before long, you're just basically staring at one little piece of a sine curve. And everything else has gotten so small that you can't see that it's there anymore. Okay, so those are the two sort of features that I wanted to point out of solutions to the diffusion equation using eigenfunction expansions. They can be a little bit rough at t equals 0 because of potential jump discontinuities between the boundary conditions and the initial condition. All right, but very quickly they smooth out, and very quickly they take on very simple shapes. Because rapidly oscillating modes decay much faster than slowly oscillating modes. Okay, can you go over how you got the general solution? Here, this? Sure. The simplest method we have to show where that comes from, well, I mean, it's constant coefficient. So actually the simplest is to say, hey, this is a constant coefficient. Let me just guess an exponential. Un equals e to the RT. And I plug that in and I get R plus lambda n equals 0. And so R equals minus lambda n. You can guess constant e to the RT or Rx, even for first order equations, if they're constant coefficients. That's the fastest way to get that solution. That's not the way you learned the first week of ODEs. The first week of ODEs, you probably learned the method of separation. You have dun divided by un equals negative lambda n dt, which is completely wrong. You can't, this is not actually a fraction. You can't actually multiply both sides by dt, but it works well enough that it's how it gets taught. What you're really doing is you're saying 1 over u sub n dun dt. And now I'm integrating both sides with dt. And again, this is not a fraction. It doesn't cancel, but it's effectively a very, very pedantic form of a u substitution, where u is u and the derivative of u is du dt dt. And so this is just natural log of u sub n, and this is negative lambda sub n t, and then I take the exponential of both sides and I get un equals e to the minus lambda n t. Right, so that's 2 ways to get that. So again, what I want to emphasize is that this is just exactly the same as boundary value problems. We've just got this extra time derivative thing here. And that is not a big deal. I just, for the moment, I pretend it's not there. I treat this as if it were a boundary value problem. I still look at the equivalent eigenfunction problem, phi xx equals minus lambda phi, with these homogeneous versions of these boundary conditions. And I find the transform associated with those eigenfunctions. I apply that transform. 2 of these things I've seen before. 2 of them are new, but easily interpreted. And after I apply that transform, I go from a hard problem to a relatively easy problem. And then I solve that ODE. Okay, yeah, it's a tiny bit harder than solving algebra problems from boundary value problems, but conceptually it's the same thing. I find the transform, I apply the transform, I solve the resulting transform problem, and then I find the inverse transform. And there it is. There's my solution. And I can code that up in MATLAB or Python and play that movie. And that's my solution. So what we'll do the next 2 lectures, I think, is just 2 more examples. We started off with a really easy example, no forcing function, homogeneous boundary conditions that don't depend on time. Our initial condition didn't depend on x. But what we'll find is that adding on to this does not really change anything. It doesn't make it any harder. It doesn't create any new problems that we haven't already encountered when we do boundary value problems. We can easily add on a forcing function here. We can easily add on non-homogeneous boundary conditions. In fact, we can make them depend on time. No problem. We can easily make this initial condition depend on x. We just have to take its transform, and none of this poses any challenge whatsoever if we understand how transforms work. And so we'll explore some of those complexities in the next couple lectures. 11:48, that kind of wraps up what I have to say. Happy to stick around for questions as usual. But if you have somewhere else to be, like the other side of your room, you're free to log off. Alex, yeah, that's fine. Just note that because I'm sharing my whole desktop, like anything you send me privately does show up on the desktop. So if it's something that needs to be private, you can send me like I could even just give you a phone call to talk about advising. Or if it's just asking like which is the best choice of classes, then that's not something that needs to be private. You can just ask.
Yeah, no, it was just about the classes. Basically, on my like advising workbook, it says I just have one class left, which is the math 4325. I think it's the modeling dynamic systems.
Uh-huh.
And it's only offered at one time. And it's also offered at a time when another one of my EMIS classes is offered. And so they conflict. And I talked to Professor Goodman. She's the EMIS advisor yesterday about this. And there's basically no other alternatives that I can take in slot for this EMIS